It's funny though. I didn't write. No, it's the most times. You need to remember as a question. And I just saw the girls see. Well, wider. Yeah. Only a few seconds. We're running back to next one. They'll make it. We're gonna make it.
Yeah.
We also think about rotation. No, on this.
Okay, page 9. Today we'll work through page 9 and 10. And then tomorrow we'll do page 11 to 12. And then I'll do morning review on Friday, 19 through 22. So on Friday, we'll have our second half of our multiple choice study. And these are the major topics that will be covered. These are the major topics that we've been covering this this spring semester. So Riemann sums. Okay. Adding rectangles and trapezoids. First theorem, second theorem, average value theorem. Integration rules such as use substitution and power rule and trig and all the different rules that we've done. Solving differential equations. Right? We just worked on that and saw that on our previous FRQ. So hopefully this is pretty fresh in our minds. And then area, volume, such as, or area, which is top minus bottom or right minus left, and then volume such as this method, washer method, and cross section. And then on your formula sheet, it's basically most of the second page. First theorem, second theorem, integral rules, area and volume formulas. Okay, so let's look at number 1. So number 1, we have the graph of f is shown between 0 and 4, between x values of 0 and 4. Let L, R, and T be left, right, and trapezoid approximation with 4 subintervals. Which of the following statement is true? And we just basically want to compare the area of left rectangle, of left Riemann sum, the actual area, trapezoid, and right Riemann sum. So I'll put that in ascending order. And because of the way that our graph is drawn, so we know a left Riemann sum, it would be upper left corner will be attached to the graph. You can kind of tell that with left Riemann sum, we should be expecting a under approximation because all of our left rectangles will be sitting below the curve. Our right Riemann sum will be attaching the right endpoint of every subinterval to our page 9, to our graph. That will be an over approximation. And if you look at trapezoids, because the graph is concave up, trapezoid is going to be slightly above the curve as well, slightly above. So we can order it this way. Left Riemann sum being the smallest because you have gaps under the curve. right Riemann sum will be the greatest because you have all these gaps above. And then trapezoid will be slightly more than the actual area because as we connect from upper corner to corner or upper point to upper point, it's going to be slightly above the curve because of the way that the graph is shaped. If the graph is concave down, then your trapezoid approximation will be under approximation. But this is a slightly over approximation, so this is going to be more than the actual area. So left Riemann is the smallest, then the actual area, and then trapezoid, barely, right? These are really, really close to each other, but trapezoid is going to be slightly more than the actual area under the curve. And then right Riemann sum is going to be the largest. Okay, number 2. For the time t greater than or equal to 0, the height of an object is suspended from a spring given by h of t. What is the average height? So we want to find the average height, given height, so we want to use average value theorem. Work it out in a separate sheet. Okay, so average value theorem. My A and B value are 0 and 2. Okay, so our A and B value are 0 and 2. Our function is this h of t. So I'm just going to put everything in that form here. We do want to work this out by hand. This is meant to be non-calculator here. So typically, when I'm working this problem, I usually wait to do the coefficient at the end. So I just have to go through this process. Make sure, though, a lot of students, when they see average value theorem, they feel like, oh, this is a lot going on, and they kind of skip some steps. And what I mean by skipping steps is students just start entering 0 and 2 into the function they see. So we have to transform this into its antiderivative before the bounds can take its role. So I want to make sure that if you see integral notation, we can never plug in anything into the expression you see. You got to go through whatever proper rules that's needed to transform this into its antiderivative before the bounds can play a role. So 16 is just going to be 16t. That's not going to be an issue. That's easy and quick. What takes a little bit more time is the fact that the integral of 7 cosine pi t over 4, there's a little bit of a messiness here. We got to go through use substitution for that. So I'm going to step to the side here and just go through use substitution for this portion, and then I'll come back to finish off the rest of the problem. So the integral of 7 cosine of pi over 4t dt. And my u value is what's inside the parentheses. So that's going to be our u value. You've got to do a whole u substitution just for that portion of the problem. du over dt. Cross multiply. Put it back into our integral here. I can pull the 7 out. Cosine of u times 4 du over pi. I push the 4 over pi out with the 7, so I get 28 over pi integral of cosine of u. And we take the antiderivative. Now everything is, let me put the du here. Everything is nice and ready. We know the antiderivative of cosine is a positive sign. And then we can bring the variable t back into our problem. So, sorry, I put cosine, for put sine there. Antiderivative of cosine is sine. Back to our original t variable, so pi over 4t. So this is the result of everything that we have here. Okay, so 1/2 times 16 becomes 16t. All this gets transformed to be 28 over pi sine of pi over 4t. And now I can evaluate between 0 and 2. Plug upper bound first, upper bound in for all the variables. If I plug 2 in for t, I get sine of pi over 2, or sine of 2 pi over 4, which is sine of pi over 2. We know sine of pi over 2 is just going to be 1, so that's nice. Cleans up nicely. Minus. And then repeat the same thing, plug 0 into everything that we see there. But 0 is going to wipe out a lot for us. 0 times 16 is 0. Sine of 0 is also 0. So all this is going to be 0. So the only thing left over are just reducing this. If I distribute that 1/2 through, I get 16 plus, and then 28 over 2 is 14. So 14 over pi. Answer choice D. All right, Eric, any questions with 2? Okay, here's number 3. Find the limit of this mess of a problem. But let's see if we can make some sense out of this. Okay, what's the first thing that we do with limit problems if it's approaching a real number? What's the first thing we do? Plug in, yeah. So let's just plug 0 in. Let's see what's happening here. So if I plug 0 in for h, I get h in the denominator. Okay, that's 0. If I plug 0 into my expression here, I get 1 plus 0, which is 1. What's the integral from 1 to 1? 0. So really, I can think of it this way, right? It's the limit as h approaches 0, this whole thing is in the numerator. And then this denominator h can be written like this. So really, I'm getting what? After direct substitution, what am I getting? Initially, 0/0. So, this looks like a mess, but the fact that we get 0/0, that allows us to apply what? What can we do if we see 0/0? We leave it like this and say that the limit is undefined. L'Hopital's rule, yeah, we can do L'Hopital's. So L'Hopital says, take the derivative of the numerator, take the derivative of the denominator, and hopefully we get another version of the expression, and that will give us another problem for us to evaluate the limit. So I need to be able to find the derivative of the top. So I'm going to indicate what I want to do. I want to find the derivative of this integral. And then separately, I'll find the derivative of the denominator. Now, this, again, I know this looks messy, but what does this remind you of? What can we do? Second theorem. We know that these operations will cancel each other out, right? And this is what second theorem says. Second theorem says if I have this one doesn't have the sorry, I put the lower bound here, but this one, the lower bound is constant. The upper bound has a variable in it, so it's just f of p of x times p prime, right? So we just plug the upper bound into the expression and then multiply it by the upper bound's derivative, and that's it. So that cleans up for us. We can do that with this expression. So we just plug that 1 plus h in for x, keep everything else the same, but we know the derivative integral notations will go away. So square root of 3 plus 1 plus h squared. All we're doing is direct substitution, right? This 1 plus h gets inserted in for the x times p prime. So the upper bound's derivative, what's the upper bound's derivative going to be? Just what? 1 plus h just becomes 1. Yep, 1 goes to 0, h goes to 1. So that's nice. It cleans up fairly nicely for us. And then the denominator gets its own derivative process. So h becomes what? Just 1. So now we have a hopefully an easier or different version of a problem for us to evaluate. So now let's evaluate the limit again, see where that leads us. And hopefully this will lead us down to a real number. Replace all the remaining h's with 0. 1 plus 0 is 0. 1 plus 0 is 1. 1 squared is 1. 3 plus 1 is 4. So square root of 4, that's just equal to 2. Okay, number 4 is also applying second theorem. So see if you can try this one. Let me write second theorem out and then have you see if you can work through this problem. if I want to find f prime will basically get rid of the integral for us. But what do we prefer with the bounds that we see if we want to fit it into second theorem? We prefer lower bound to be what? Or what do you see here between 0 and tangent of x? One is a what? Or what does a and p of x represent? A is the what? Constant, yeah, and p of x is the variable. So I think it's just nicer to just fit it into the form that we want. So we can adjust the bounds, put the tangent up top, but can I just flip the bounds and just not do anything? If I change the bounds, I also need to make an adjustment with what? Because I'm kind of changing the problem, right? If I just adjust the order of the bounds, I'm changing the problem. What can I do to make it so that I'm balancing things out? Make it negative, yeah. So let me rewrite the function as this. Integral from 0 to tangent of x, negative dt over 1 plus t squared. Okay, so now looks like we can go through f prime. We'll take the derivative of this. Now this should match up nicely with the form that we have. Everything matches nicely. We just have to follow the rule. So f of p of x, that just means insert the upper bound into the expression exactly. Sorry, I wrote dt twice. That shouldn't be. Should be only once. So tangent gets inserted to the variable, but we keep everything the same. But we're not done yet. We still have to worry about this p prime. So p prime is asking for the upper bound's derivative. So what's tangent's derivative? Secant squared, yeah. So this is an acceptable answer, but this is a multiple choice question. So what they're doing is they're using properties to simplify it even more. And there's a trig identity that says 1 plus tangent squared is equal to secant squared. So technically, we're getting negative secant squared over secant squared. And that's why the answer choice ends up being just -1. Hey, page 10. The graph of a differentiable function is shown if h is the integral of f, which of the following is true. So h is basically the area or displacement between 0 and x. wherever that x is, or in this case is h of 6. And then they're asking about h prime and h double prime. So let's build out the other functions that we need. Let's build out h prime and h double prime. So we know that h of 6 is just the integral from 0 to 6 of f of t dt. Let me build out h prime first. So h prime is just asking for the derivative of this. And that's basically second theorem again. Anytime you're pairing derivative and integral to each other, they're going to cancel each other out. The upper bound gets inserted into the t, and then times the upper bound's derivative. So f of x times 1, that 1 just goes away. So it's just really just f of x. All right, we're basically taking something that is one level above f and moving it down to the level of f. And which means that h double prime of x will simply be f prime. So a staggered relationship here. Okay, so h prime of 6 would just be f of 6. H double prime of 6 will just be f prime of 6. So let's see. The integral from 0 to 6, all this is below the x-axis, so we should expect this to be some negative value, right? I mean, if we just draw a rectangle here, we can kind of have an idea that the area is probably somewhere around negative 15, maybe a little bit less. That's just a really rough estimation, but it's a negative value. H prime of 6 is f of 6. F of 6 is just this number here, and f of 6 is just 0. H double prime of 6 is f prime of 6. F prime of 6 is asking for the slope, and this looks like a slope of 1 or 1/2. We don't really know, but we know it's greater than 0. So we're comparing a negative number, 0, and a positive number. We should be able to put them in ascending order. This is going to be the smallest, followed by f of h prime of 6, and the greatest value will be h double prime of 6, which is the slope of f, which is a positive value. Okay, a lot of second theorems here. Number 6, we have a function defined. F of x is the depth integral from 0 to x of 2t cubed, on which of the following interval is the graph concave down. So concave down, you know, it has to involve the second derivative. So let's see if we can work our way down to the second derivative. First derivative is just basically going to wipe this integral out and take something that is a level above the function and bring it down to the expression we see in front of us. So f prime is just going to wipe out the integral for us. That's the second theorem. The only thing it's going to do is going to replace the t in terms of x. So f prime is really just the same thing as the function, just with the integral removed, right? The integral places this expression a level above it, and now we're just back down to this level of 2x cubed. So this is basically f prime. So now f double prime, now we can involve power rule. Now this is going to be a standalone term. We can now go through power rule to move down to f double prime. So 2x cubed becomes 6x squared, 30x, 36. Okay, so now let's go through our full steps of test for concavity. So find our critical points, set equal to 0, find our critical points, populate our concavity sign line, test each subinterval, and look for intervals of concave down. Okay, try this one. See if you can work your way through this one. So I'm just choosing test points so I can gather information about concavity. I'll plug 0 in to the factored form here. 0 minus 2, 0 minus 3. That's two negatives. That gives me positive. Second derivative. So positive means concave up. 2.5, and it's a test number that I can use. It's between 2 and 3. 2.5 minus 2, that's positive. 2.5 minus 3, that's negative. Positive and negative is negative. So concave down. Plug 4 in. Positive times positive is positive. So concave down is going to be in this interval from 2 to 3. Number 7, another second theorem. See if you can work your way through. Second theorem is asking for the derivative of some definite integral of some function. Okay, here's second theorem, which is following what the rule says. Upper bound gets inserted into the expression. Just direct substitution. We don't do anything with this expression. We don't do derivative at all. We just plug it in. The only derivative we do is with the upper bound, so times 2. Number 8 takes advantage of that formula that we've been seeing with particle motion, which is final equals initial plus displacement. So if we're looking for a point and they give you a point and they give you something that is at the derivative level, we can go through that final equals initial plus displacement to kind of work our way through. And this is a calculator question, so we can just set it up and put it in the calculator. So let's try number 8. So it says that G is the antiderivative of F. So G is the antiderivative of F. What that means is that F is really at the G prime level, right? If it takes the integral of F to make it up to the same level as G, then we know that this F is really G prime. So we know that another way of saying this, okay, we know this is just another way of saying G prime. And they give you an order pair at the G level, and they're asking you for the order pair at the G level. So we know that we can go through this formula here, which is if I'm looking for a final position, I just have to start with the initial or given position plus however much progress I want to make. Sorry, plus displacement. I'll put the formula next. So this is the formula that I usually use, and then we can adapt it for our problem. F of B is equal to F of A plus the integral from A to B of F prime. So this is my starting point. This is however much progress I'm making, and this is where I'm going to end up. So in this case, if I want to find G of 3, I'm going to start at G of -1 because that's what's provided for me. And then I just have to figure out how much progress I've made between -1 and 3 under my G prime. This we can't do by hand, so we'll plug this in the calculator. We know this is just going to be -2. This is going to be however much progress I make. And I'll add these together to figure out my final destination. Okay, so we'll do math 9 for that. All right, any questions? So no homework tonight. We've gone through pages 9 and 10. What I'd like for us to do is tomorrow, I'll just start off working through page 11 and 12. We should be able to get through all those pages. And at the end of class, I'll just check pages 9 through 12. And then your test, part 2, is going to be on Friday. And then I'll work through pages 19 through 22 from morning review, or you can use those pages to practice on your own. Okay, come get your phones. Great, thanks. We finish these problems to show them all. Thanks. Okay, thank you. Okay, thank you. Yeah, just finish that show me tomorrow.
I didn't watch it. Sorry, I'm plugged by myself.
Okay, great, thank you. Yeah, sure. Yeah, we'll just go through tomorrow. Yeah, tonight or today I did page 9 and 10.
Okay.
And then tomorrow in class we'll do 11 and 12. So we should be able to get all done. So we can just finish up 9 and 10.
Okay.
And then tomorrow in class we'll do 11 and 12. And then 13 and 14, I'll need to do this as well. This is part of homework from so just, yeah, just finish those pages and I'll check it tomorrow. Thank you.